Hey folks, in this video we're going to talk about a set of very important chemical reactions called redox reactions for short, otherwise known more formally as reduction-oxidation reactions. What does that mean? What are we talking about with reduction-oxidation? Well, we're going to talk about that in this video. So we're going to start out by just kind of reviewing basic electronic properties of atoms and how ions are formed and what kinds of ions tend to be formed depending on the particular element and the position in the periodic table. And then once we have those basic definitions reviewed, we'll define what we mean by oxidation reduction and look at a couple of very simple oxidation reduction reactions. We'll finish off by just talking about a simple battery because batteries are electrochemical reactions that are based on the reduction-oxidation process. All right, so here's a periodic table, as you all know and love. And as you know, you can see here, basically, we've got over here on the left side of the periodic table, we have our metals, all right? The transition metals, of course, here in the middle. And then on the right side of the periodic table, we have our nonmetals. We've talked about this in past videos, of course. This column here, 8A, over here on the right, of course, are the noble gases, which are very unreactive species. Okay, so let's talk about the electronic properties of atoms and what's important. It turns out that when we talk about chemical reactions, of course, and again, we've talked about this in the past, so this is just review. Chemical reactions are basically reactions involving rearrangement of electrons. And when we talk about rearranging electrons, it's going to be the electrons that are the outermost electrons in the outermost shell of the atom that are the most important. They're going to be the ones that are going to react first. We call, of course, those electrons in the outermost shell, we refer to those as valence electrons, right? And our chemistry, of course, is dependent on valence electrons. Now, you know in the periodic table that when we look at a particular column in the periodic table, we're talking about a family. For example, here in column 1A, in column 1, the distinction here between them, of course, is that as we go down the column, we're adding electrons to shells that are farther on average from the nucleus. But the distinction here is in a family, we know that the chemistry and the chemical properties of the elements within a given column are very similar. Why are they similar? They're similar because they have the same number of valence electrons. Even though the total number of electrons differ as we go down a column, the number of valence electrons will actually be the same. So when we look at column 1A, as we go here in column 1A, we're going to note that lithium has one valence electron, sodium has one valence electron, potassium has one valence electron, so they're all very similar. Let's move over here to column 7A. Fluorine has 7 valence electrons, chlorine has 7 valence electrons, etc. In the noble gases, we're talking about valence electrons as having 8 valence electrons, and it's that magic number 8 that we find, as we've discussed, that is kind of the goal. The noble gases are unreactive because they have full subshells of electrons. Things obviously get more complicated as you get to higher atomic numbers with more electrons, but we're not going to go into that here in this particular video. But basically, it's the full subshell of the noble gases that make them very unreactive. Their subshell is full. They don't want any more electrons. They don't need any more electrons, so they are not going to react. Whereas the other elements in the periodic table are trying to achieve that goal of what we call a stable octet in those situations. And again, just examples here. We talked about fluorine and chlorine. So fluorine here has an atomic number of 9. The neutral atom is going to have 9 electrons. But of those 9 electrons, it's 7. We can count over here from the left. 1, 2, 3, 4, 5, 6, 7. And that's why I like the numbering of the periodic table to be in the A and the representative groups 1, 2, 3, 4, 5, because it does indicate the number of valence electrons. Of course, down here in the transition metals, things are more complicated. But in any event, we have 7 valence electrons in fluorine and 2 in the inner shell, n equal 1 shell. Chlorine adds a shell. We're going down to row 3 of the periodic table. So we have 3 shells that we're talking about. It has 2 electrons in the n equal 1 shell. The n equal 2 shell is completely full with 8 electrons. The n equal 3 shell has 7. And again, the valence electrons with fluorine and chlorine have the same number of valence electrons, and that means that they have very similar reactivity. All right, so we've talked about this. I just mentioned this, and we talk about formation of ions. All right, the elements will gain electrons or lose electrons in order to achieve a more stable configuration, and basically it's a full subshell configuration, a noble gas configuration. And so what that means is that whether it gains or loses electrons is going to depend on where it appears in the periodic table. Metals tend to lose electrons. Nonmetals tend to gain electrons. If we go back here to this periodic table here, that means that, for example, if we're looking at sodium, which has 1 valence electron, if it loses that 1 valence electron, then it's going to have an electron configuration that's identical. So it's going to have 10 electrons then. So it's going to have an electron configuration that's going to be the same as neon. Right? So it loses 1. That means it's going to be a cation. It's going to have a positive charge, and its positive charge is going to be +1 because it's losing 1 electron. All right? It still has 11 protons in the nucleus, but only has 10 electrons. So it has a +1 charge. Okay? Magnesium will lose 2 electrons to achieve that neon configuration. All right? So it's going to have a +2 charge. Right? It's going to have 10 electrons but 12 protons. So it's going to have a +2 charge. Going over here to the right side of the periodic table, fluorine is going to gain an electron to be like neon. Right? And so it's going to have a -1 charge because it's going to have 10 electrons but only 9 protons. So it's going to have a -1 charge. Oxygen is going to gain 2 electrons to have 10 like neon, so it's going to have a -2 charge. So those are the ions that are typically formed from those representative elements. Again, the transition metals tend to be a little bit more complicated, and we're not going to go into those. All right, so this is a little table here that kind of shows that the ions that are formed by the most common ions formed by these elements indicates their charge. And again, as we noted here, that we're going to have in this particular column, all right, 7A, we're going to have gaining 1 electron, so we're going to have a -1 charge. In 6A, 2 electrons have a -2 charge, 3 electrons for nitrogen and phosphorus, for example, to have, again, all are aiming for this 8 electrons. And we'll note here in column 1A, 2A, column 1A tends to lose an electron to have a +1 charge. 2A will tend to lose 2 electrons. 3A will tend to lose 3 electrons, like aluminum +3. Again, if you look here at the transition metals, at least the ones that are listed, you can see the most common ions that are formed, and it's not so clear-cut as it is in the representative elements, but again, we're not going to go into that at all. Okay, so those are the basic ions that are formed. So let's get into this whole business of reduction and oxidation and redox reactions, which form a very important class of reactions. Reduction-oxidation reactions occur. They are responsible for life. I mean, what's going on within your body to keep it going, to generate energy, is reduction-oxidation reactions that are going on within your body. You're inhaling oxygen. Okay, what does oxygen do? Oxygen oxidizes things. So these are reduction-oxidation reactions occurring in your body. Combustion reactions are reduction-oxidation reactions. In fact, you could say that what's going on within your body are little tiny combustion reactions to generate energy to keep you going. So these are an important class of reactions. So what are we talking about? So we talk about reduction here. What we're talking about is a process where electrons are gained in a reaction. All right. And so reduction involves the gaining of electrons. Oxidation involves the losing electrons. So as you might expect, in a very simple analysis here of a very simple reduction-oxidation reactions, basically what you're seeing is that one substance is gaining electrons that the other substance is losing. Simple as that. All right. And of course, this is a simple explanation for batteries because that electron transfer is occurring through an external circuit. So we're talking about a substance being oxidized is losing electrons as electrons, at least in a simplistic example, because we really talk about electric fields, those electrons are traveling through that external circuit from the oxidized, the species that's undergoing oxidation, to the species that's undergoing reduction. And that's how we get electrical current. So redox reactions are the possibility. You have to have both. You can't have just oxidation because if something's losing electrons, something has to be gaining electrons. So in a reduction oxidation situation, you're going to have both. One species is losing, the other species is gaining. Simple as that. All right. So we talked about metals having a tendency to lose electrons. So here are some what we call half reactions because, as I mentioned, a reduction-oxidation reaction has to have both. So these are oxidation reactions that are occurring. And in these oxidation reactions, we're seeing that we're losing electrons. So, for example, iron here, this is iron, Fe, is losing 2 electrons. Okay. It is losing 2 electrons, and that's an oxidation process. It becomes iron plus 2 when it loses 2 electrons. All right. Iron plus 2 can also lose an electron and become iron plus 3. Sodium, as we mentioned, has a tendency to actually lose 1 electron, and so here's the oxidation of the sodium. All right. Sodium is very, very reactive because of this tendency to lose an electron. If you've probably seen videos, if you haven't, look them up on YouTube of people throwing sodium into water. It's highly reactive, and it's quite an energetic reaction that's going on in there. Aluminum has a tendency to lose 3 electrons, and in fact, aluminum undergoes oxidation so readily that when you have like an aluminum can or something like that, that an aluminum will oxidize so rapidly to form aluminum oxide that actually what's on the outside of the piece of aluminum is a coating of aluminum oxide, which helps to protect the aluminum. So rust formation is a situation where we talk about which is oxidation of iron. And to form iron oxide. And when we talk about a galvanization process, we're talking about coating iron with a material like zinc, because zinc will oxidize more readily than the iron, and that helps to protect the iron from being oxidized. There's some interesting experiments you can do with that to test that out. All right, so reduction, we have the same thing. Nonmetals have a tendency to gain electrons, and here are some examples here. As you can see in this situation, that in each of these cases, and actually I would say nonmetals have a tendency to gain electrons, but I've actually showed here also situations where the ions, copper ions, would be reduced to form copper. Okay, and we have here a situation where it could go from gain 2 electrons to form copper metal, gaining 1 electron to form copper plus, and then iron can also gain 2 electrons to form iron. So that's a situation where we have reduction where we're gaining electrons in these situations. Now, the ability of a substance to gain or lose electrons has some very important characteristics. Important when you put two metals together, then the properties of those metals might be such that one substance might gain, the other substance might lose those electrons. If you take a solution, for example, that has copper ions in it, because when metals dissolve, if you have a situation where you have metal ions in water, it's going to be the ions that are formed. If you were to take a solution that had copper ions in it, and for example, you dropped an iron nail in that solution, one that's not galvanized, if you dropped an iron nail in that solution, what you're going to find is that the iron oxidizes more readily than the copper ions, and the copper ions will very quickly steal electrons from the iron, and they'll form copper metal. And when that happens, then the nail starts to dissolve because they'll steal the electrons from the iron as a result. And you'll see the nail starting to dissolve. You'll actually see a copper metal coating starting to form on that nail. And so that's, a situation which is an example of reaction. So we might see here that, and there's a typo in this particular slide. But in any event, when we have a situation where this reaction here that's shown here at the bottom, we have zinc solid, and when zinc solid is put into a solution of copper ions, all right, what happens is, again, the zinc oxidizes more readily. So this is actually copper solid there. That's what that's supposed to be. And so the copper ions will steal electrons. They'll be reduced to form the copper metal. And the zinc metal then loses 2 electrons to become the zinc ion. So the zinc is being oxidized because it's losing 2 electrons. And the copper ions are reduced because it's gaining 2 electrons. And so that's where that's an example of a very simple reduction-oxidation reaction. The zinc is losing 2 electrons, the copper is gaining 2 electrons. The copper ion is reduced, the zinc metal is oxidized in that situation. And here's an example of a very simple battery. It's called the Daniell cell. It's a very simple battery based on that reaction. And so what we have here are solutions in this particular battery. Over here on the left, we have a solution that has zinc ions in it, and it has an electrode that's zinc metal, okay? And on the other side of this battery, we have copper ions in the solution, and we have an electrode that is copper metal. And so what happens when we have these solutions separated, the reaction can't take place between these 2 species in solution. The only way this works is for the zinc, which, remember, the zinc is oxidized, right? We look at the reaction down here. The zinc is losing electrons, and the only way for this to happen is for the electrons to flow through an external circuit to the copper electrode, and then the copper electrode and then what happens is the copper ions are reduced. So the electrons flowing from the zinc as it is oxidized through an external circuit, all right, to the copper electrode, which then those electrons, if you want to imagine these electrons, are transferring from that electrode to the copper ions in solution to make copper metal. All right. So simple, zinc's oxidized, the copper ions are reduced. the electrons are transferred through an external circuit. That's a battery. That's how a battery works. It's a simple battery. That's how it works. Of course, batteries are really important these days. There's a lot of really, really important research. If there's a research topic you want to dig into, research on the development of new batteries, because they're useful. Obviously, if you're watching this on a computer, it's got a battery in it. All right, what we want are batteries that are energy efficient, that can last long. And actually, the other issue with batteries is environmental issues associated with batteries. The disposal of batteries is a problem, right? The mining of the materials to make a battery can be an environmental problem. So there's a lot of research being done to find materials and battery to make batteries that are more environmentally friendly, that can generate more energy, that can last longer. Very, very important research in these areas. So again, if you want to dig into something, try digging into battery research and find out what's going on out there. A lot of really neat and important developments in batteries these days. All right, so this ends our short discussion on reduction-oxidation reactions. As always, if you have any questions, let me know.